Hi guys, welcome back. This is our final lecture on finding large prime numbers, or finding prime numbers in general, but it's efficient so we can find large prime numbers this way. And this, in fact, not is it only our last lecture on finding large prime numbers, but this is our last lecture for advanced topics in math, spring of 2020. So this is it. We are going to use what we have learned about the Jacobi symbol and about calculating the Jacobi symbol in order to devise a yes-based Monte Carlo algorithm with error probability of at most 1/2. Okay, so let's see how this works. Okay, we are going to suppose n is odd. Okay, suppose, because we are not going to test even numbers for being prime. So suppose n is odd. Okay, and so what do we know? We know that the Jacobi symbol can be computed in the following manner. A to the n minus 1 divided by 2 mod n for any a. Okay, so just as I'm going here, I'm thinking when I say suppose n is odd, we're going to see in the algorithm, and this is true for I mean, it's true for all n, but in the algorithm that we're going to be seeing, suppose n is odd. So I am choosing an n. So I'm thinking of myself in the algorithm mode. I'm choosing some n, choose some n, and I'm wondering, is n prime? That's what our algorithm is going to be asking. And so now I'm saying, okay, let's take this n, and we know that we could calculate the Jacobi symbol like this. And I'm gonna point to you that we don't want to factor n. Okay, so we want to avoid factoring n. I mean, that is the whole thing. If we could do that, then I mean the whole RSA wouldn't be secure. So it does make sense. So we're going to be choosing these large values of n and wondering if they're prime. We can't factor them to figure that out. So we have to have a different way of determining whether the number is prime. That's what this whole thing is about. Okay, so I'm writing out a couple of facts here. Suppose we have a value of n that's odd, and we calculate the Jacobi symbol like this. Okay, that's a this is this is here. Actually, sorry. Let me be extra clear. This we calculate the Jacobi symbol like this, and that is true for any a if n is prime. Okay, we can make this calculation for any n, and this relationship will be true if n is prime. Okay, so let's be really clear about that. The n is odd always, and then we've chosen this value of n. We're going to make this, we can make this calculation right here, and we can make this calculation right here. And these will for sure be equal if n is prime, no matter what value of a I choose. Okay, if n is composite, then maybe it's possible that this will be equal to this. Okay, maybe. Okay, so if it's true, if for n composite, if for n composite this congruence holds, okay, so if this is true and n is composite, then we call n a pseudo prime to the base a. Okay, all right. Let me just give you an example of a pseudo prime. Example. Okay, yeah, let's just do this. Example, 91 is a pseudo prime to the base 10. Okay, 91 is not prime. 91 is 91 is 7 times 13, so it's not prime. And if I make the calculation of the Jacobi symbol like that, I get this. Okay, and that will be the Jacobi symbol will be equal to 10 to the 90 divided by 2 mod 91. Okay, so check that out. In this case, so in this case here that the example I've given you, n is 91 in my notation here, and a is 10. Okay. So we have that possibility, and this can happen for. So this is so we either, if we get an equality, if we calculate this two different ways and we get an equality, then we either know it's prime, or we have that it's a pseudo prime, or it doesn't equal, and then we for sure know that it's composite. Okay, so getting the pseudo primes will happen at most 1/2 the integers a. Okay, this will happen. So we'll hit a pseudo. We'll make a conclusion that it's prime when it's not, approximately 1/2. Well, at most 1/2 the times. This will happen at most 1/2 of the integers a in Zn star. Okay, so what I highly suggest you do is take a look at this example, expand on this example so you can see what's going on. Okay, take n equals to 91. Okay, and then take a in, choose just pick an a in Z91 star. Okay, and then make the calculation, this calculation. Okay, and see what numbers you get, and vary a. So like try various numbers of a and see what happens. Okay, so make that calculation a bunch of times. You could look up if you wanted on the internet. You don't have to do this, right? You don't have to do, I mean, on the exam you'll need to do the steps of this calculation by hand, so I can see that you can do it. But for the purpose of experimenting around, go ahead and just Google like Jacobi calculator or Legendre calculator, and you'll find that. So you could look like, you could Google this Jacobi calculator, and then you'll get something where you can just enter a and n, and it will tell you the value of the Jacobi symbol. Or you could, I haven't tried it, but you could try Wolfram Alpha and put Jacobi of and see whether it works. I have not tried that actually, but maybe that will work as well. It's usually pretty good. Okay, so you can have some method of making this calculation. So what I want you to do is for the value of n equals 91, pick a whole bunch of different values of a, calculate the Jacobi symbol, and watch what happens. Okay, then take a number that you know to be prime. So let's take something we know to be prime. Let's say, is 53 prime? Let's see, 53 I think is prime, right? Okay, so this is, take a prime number like that, prime, and then it doesn't have to be 53, but pick some prime number, and then what you need to do is take values of a in Z53 star like that, and then compute the Jacobi symbol for a whole bunch of values of a. Try various ones. Okay, you will see what happens is you don't get two answers. You'll always get the same answer. Okay, so try that out. And then this will give you some amount of intuition about what the algorithm is doing, which is important because it's very straightforward. When I write the algorithm out, it's like about 5 lines. I'm about to do that, but you want to have intuition about what's going on. So just compile a little bit of a table for yourself. Maybe even do a couple of other numbers. Play around with the symbol and see what the symbol is for various values of a when n is prime and when n is not prime, and see which numbers are pseudo primes and which numbers are not. Okay, that's important. Okay, and my claim is that you will hit on when n is not prime, you will hit on a pseudo prime at most 1/2 the time. You could even try with some smaller values of a not prime number, like I don't know, 7 times 3 or something, 21, right? Like you could try with n equals 21. You could try all values of a between 1 and 21 and see what happens. But really, just spend like half an hour playing around with it, and then you'll have a good sense of what's happening here going forward. Okay, so finally, in the tail end here of our 4th lecture on finding prime numbers, here comes the Solovay-Strassen algorithm. Finally, we have the Solovay-Strassen algorithm. Okay, it is a yes-based Monte Carlo algorithm. It's a yes-based Monte Carlo algorithm with error probability at most 1/2. Okay, here it goes. So I'm going to write it out in sort of a pseudocode here. So I'll just call it Solovay-Strassen. And it takes as its input n. So what in practice is happening here is n is chosen randomly 100 digits long or 200 digits long, and it's odd. So this is the number you're testing. So you want to know, is the basic question is this prime? So we don't have we're not what we're doing is we're just going to say, okay, fine, give me a random number and I'll test to see if it's prime. We already saw a couple of lectures ago what the probability of a randomly chosen value of n is to be prime given the size of it. Make sure that you understand that. That came from the prime number theorem. Okay, so we're going to randomly choose this value n. It's going to, in practice, be very large. For us working on an exam or with an assignment questions here, n will be smaller so that we can keep a handle on things. But the idea is we get this large value. We were hoping that we luck out and pick a prime one. So we've picked this large number. Now we're asking, we want to know, is it prime? Okay, so but we don't. Okay, so we want to know, is it prime? That's key thing that we want to know. And we want to know, what we want also is we're not allowed, or we are not able, really, in fact, not able to factor n. That is a key point, right? The number is large, factoring is too time consuming. We're not factoring. Okay, so we want to know, is it prime? And we're not able to factor to try to check that. So that's what this is all about. Okay, so we're going to choose random A. Okay, this is exactly what we were looking at above. Choose random A, where A will be between 1 and n minus 1. Okay, so we're going to choose this random value of A. We will compute the Jacobi symbol. Okay, so this means X will be assigned the value of the Jacobi symbol. Okay, now this step right here, it must be computed efficiently, and that means without factoring. And we learned how to do that using the features of the Jacobi symbol. And the key to that is the quadratic reciprocity. So the previous video, we learned how to calculate Jacobi symbol without factoring the number that's on the bottom, right? That is this number. We're not allowed in this algorithm to factor that thing. In finding the Jacobi symbol. That would be one way of finding the Jacobi symbol, but we're not using that way. Okay, we are not going to factor n, so the Jacobi symbol here must be computed efficiently, which means basically without factoring. Must be computed without factoring. Okay, then if X is 0, then that's it. It's composite, right? I mean, that's our thing. If if the Jacobi symbol is 0, that is telling you that the and is composite. Okay, and that is not going to be an error. So you're done with that number n. You're finished. Okay, so you randomly selected a number. You did this one step of your algorithm. You found out, oh, the Jacobi symbol evaluates to 0. Therefore, I know that n is composite. I'm finished. Okay. Right. So then you throw that n out and you pick another n and you try again. Okay. If it comes back, so now we are now in the case where the algorithm is going to continue. So that means that x would be 1 or minus 1. So we now continue, and then we compute y, and we compute y in this manner: a to the n minus 1 over 2 mod n. Okay, that can be done without factoring n. So we don't know if n is prime or not. Okay, we don't know. Okay, that's what we're trying to figure out. What we do know is that the calculation we've previously made, well, let me write it this way actually. X will equal y. X equals y if n is prime. That's for sure. Okay. Also, sometimes x will equal y when n is not prime. That's if we have hit on a pseudo prime a. So n would be then a pseudo prime to the base a. Okay, so we check if x is congruent to y mod n. Okay, we're going to check. And if it is, we return prime. Otherwise, we return composite. And then our algorithm ends. Okay, so what can happen here is if we do this, we are going to be correct. Okay, and if we do this, we are going to be correct. If we do this, if we end up returning here, what could happen? There's two possibilities that can happen here. N could be prime, or n could be a pseudo prime to the base a. Okay, those are the two possibilities, and this can happen with probability 1/2. So that's the 1/2. That's the probability that could happen. Okay, so we want to know obviously if it's prime or not. And now we've returned. Okay, so we throw out the number in either of these cases. We throw out the number and we start again with another enter. If we come out of the algorithm with a sort of a positive outcome, then what do we know at the end? Then we know, therefore, we know n is prime. Let me try that again. We know n is prime with probability 1/2. Okay. All right. So then at that point, that's not very good. We want to gamble on with only a 50% chance of winning, right? That's not how you go to Las Vegas if you're only going to win 50% of the time. So what you want to do now is you're like, okay, I know that I know n is prime with probability 1/2, and I use some value of a, right? I used some value of a between 1 and n minus 1. So now what I do then is I choose another value of a. Choose another value of a. And I keep my n because I'm getting this n is so far not rejected in some sense. I choose another value of a. I keep the value of n. Okay, and I run the algorithm again. and then I will get, if I get a yes, that is on a different value of a, I will, if I get a yes, then the probability that this number is prime has now increased to 75% because my error is a 1/2, and then my error the second time is 1/2, and the two n values are independent. These are independent events. So the error after running the algorithm with two different values of a, I run the algorithm twice, each with a different value of a, and I get a probability of error of 1/2 each time. So then the overall probability of error is now 1/4. So now I know that n is prime with probability 75%. Okay, so we can just keep doing this. So as soon as we get a composite return, then we're like, too bad, and we throw it out. We pick another one and we start going again. Okay, we only have to you have to pick so many, you have to run so many times, according to the prime number theorem, until you have a probability of picking one that's prime. But as soon as you get one that's prime, the first time you go through the algorithm, the error will be 1/2, and then the second time the error would be 1/4. Then the third time you go through, the error will be 1/8, and then the fourth time you go through, the error will be 1/16, and you can keep doing that until you get the probability of error so low that it's equivalent, say, for example, to being hit by a meteorite. And at that point, you're like, okay, I'm willing to run with this. I might be wrong. I cannot be 100% sure, but it's just as likely as getting hit by a meteorite, and I never worry about that. So then I just move on, declare it to be prime, and I'm finished. Okay, so that is the idea. It's a probabilistic algorithm. We're never 100% sure. The upside, what are we getting about never being 100% sure? What we're getting is speed. Okay, so we run the algorithm m times. You can pick m yourself. So, you could calculate m. If I want an error of less than 1 in 1,000 or 1 in 10,000, what value should m be? Why don't you answer that question for yourself? Like how big is m to be confident the probability of error is less than 1 in 10,000. Okay, and so the error bound, we run m times and this is the error bound we're going to use. It's basically 2 to the minus m. Okay, so it's actually a little bit better than that. I'm going to tell you what it is, but when we're doing calculations, we can come close enough with the 2 to the minus m. So it's 2 to the minus m. Okay, and just for completeness, because I feel I have to do this, what it is, actually it is this log. It depends a little bit on the size of n. It's a log of n minus 2 over the log of n minus 2 plus 2 to the m plus 1. Okay, it is effectively this, especially as n gets larger. Okay, so we're going to use that. The complexity of this algorithm, the complexity of the algorithm is a big O log n squared. Okay, you see where the log n is coming from is because we are doing the modular exponentiation. Okay, and we are doing it on size of n over 2 effectively. So that's where the complexity bound is coming from. So let's the final thing we'll do here is let's just take a look at what happens as you run the algorithm. So you are looking at what is the probability of having an error, and you're going to run the algorithm once, and then I'm going to calculate here 2 to the minus m, and then I'll have the tighter bound. So this is the probability that you're wrong here is 0.5. Okay, then you run the algorithm a second time, and the probability that you're wrong is 0.25. And I'm going to expedite things here. There's obviously, then you run it 5 times, and then the probability that you're wrong is 0.312 times 10 to the minus 1. So that's 0.03. I have to, it's basically like this, 312 like that. There's undoubtedly there's a 5 there. So you're now basically 3 in 100 possibility that you're wrong. So you just keep putting this thing up till you feel comfortable. So that is going to be, if you run it 10 times, you can do these calculations yourself. Make sure that you get the same numbers. So that is 10 to the minus 3. And then if I run it 20 times, I would be here times 954 times 10 to the minus 6. So here, we're roughly here 1 in a million chance that when we say the number is prime, it is actually not prime. That's not so bad, 1 in a million, but we don't have to stop there. We can get any desired level of accuracy, just a matter of weighing off how much accuracy you want compared to how much time you want to take running the algorithm. Okay. It's not, however, the time complexity of the algorithm is not that bad. It's log n squared. At least it's got that log of n in there, and so you can. And when you run it 50 times, you're only multiplying by a constant. So okay, so let us see if we did run it 50 times, we would be here 8 I got times 10 to the minus 15. So here the probability of an error is approximately 1 in a billion. And then if I were to run the algorithm 100 times, I would have an extremely small number here, 7, 8, 9 times 10 to the minus 30. Okay, so at this point here, the probability that I'm wrong when I tell you that n is prime is vanishingly small. I've had to pick, to run the algorithm 100 times, I would have to pick 100 values of A. That's what I'm doing. I'm picking 100 values of A when A is between 1 and the prime number, and I'm computing A to the n minus 1 over 2, and I'm computing the Jacobi symbol without factoring the n, and I'm asking, are these things equal? And basically what has happened is the algorithm has identified, or the calculation has been done 100 times, and 100 times the calculation has come back and said, yes, these things are equal. Meaning that I have either in my 100 chances of picking A, I have not hit on a pseudo prime, or in fact that n is prime. One of those two things has happened, and by the time I've done it 100 times, the possibility that I incorrectly say n is prime when it is not is extremely, extremely low. And of course, if you're not happy with that, you can just keep going. But you can never be 100% sure. This is not a deterministic algorithm. It is a probabilistic one, but it works extremely quickly. Okay, folks, that is all. So these 4 lectures together alert you to how to use the number theory that we've just learned in order to find the large prime numbers efficiently, which of course you need for the RSA encryption algorithm. Thanks, guys. Good luck with your studying, and it's been a pleasure teaching this course. Bye-bye.